Guten Tag, wie geht's? Ich heiße Guy. Ich habe Deutsch in Schule gelernt im 83. Also, the rest of this presentation will be in English. I'm glad you're laughing. Dragging C++ into the modern era, a proposal for a 2D graphics API. So here's the summary. I'm going to give you a lightning tour of computer displays in 10 slides, from the esoteric to the mundane. And after that, we'll look at the proposed standard graphics API. That will be a lightning overview. It's a 160-page paper. We're just not going to cover that in this kind of time, nor would you want to, really. Then I'll quickly take you through the demo game that I've not really finished writing, but it exercises the graphics API very well. Finally, I'll give you a shopping list of things to do and how you can help, should you want to pitch in and join. There's still a lot of work to be done. Before we start, I want you to raise your hands if you were using computers in the first decade of this century. Okay, lots of you. What about in the 90s? Ooh, 80s? Ooh, 70s? Oh, come on, really? Okay, I will spare your blushes. So Claire, and your name, madam? Anieda. So using computers in the 70s, what was that like?
BBC microphones in the fifth form at school.
Ah, that was 1981. I want the 1970s. What about the Commodore PET? Oh, so that was 1978. I think that came out. Right. So that was great big screen and a keyboard at the front, and they were what was the user experience like? How would you compare the user experience of a Commodore PET from then and now?
It was amazing.
Why? So was it amazing because it did exactly what you expected it to, or was it simple? Or
I had no expectations.
Yes, I suppose your first computer, you always think, this is going to be brilliant! And it always is, isn't it? Right, okay. Who can tell me what this is? Right, oh, before we start, was anybody at my talk in Poland? Nope, good, all right, because most of this is taken from my Poland conference. So if you had seen it, please don't shout out the answers, but that's none of you. So this is the Univac 1 console. That picture dates from 1951, okay? So the display is simply, it's an irregular mass of lights, really, isn't it? It's just bulbs that just light up in random places. The characters are shown by a combination of two lights. If you see that white rectangle in the middle, you'll see that there's a column of 4 lights on the left, and there's a row of 12 lights in the middle. And so you choose a character, or rather a character will be shown to you by highlighting 2 of those lights. And also notice how the inputs are mixed in with the display. Those little black toggle switches, they're amongst the display. So the view and the control are not separated, which is very poor. But it's not really a display as we know it. These are feedback lights. It's probably, I'm not being especially honest. This, on the other hand, who can identify this? Ooh, you're all young folk, aren't you? This is the Ferranti Mark I. This particular model dates from 1952. Those 6 circles that you see are actually the ends of what are called cathodic tubes. And each of those displays 64 lines of 64 dots, which was actually enough to display a checkerboard and play checkers. The first computer game, well, I think it's the first computer game, was a game of checkers written for this machine. This one? No one? Oh. No. MIT, no. Well, there probably was one at MIT, yes, but they were all over America. This is the DEC PDP-1. That circular display is very futuristic. It's a very... it was on this machine that Space War was created in the 1960s, which is often cited as the first computer game, but as we all know now, It wasn't. It's hard to find good images of space for. If anybody can, happens to have any, or happens to have a father or a mother who was working in computing and has pictures of that, I'd be really pleased to see that sort of thing. So space war in the PDP is significant because it heralded an era where programmers learnt their craft just by writing simple games and puzzles and fairly trivial applications, because computer time suddenly started becoming a little bit cheaper. So programmers were able to waste that time effectively on learning, but without a particular focus and without risk. The worst place to learn the art of programming is probably whilst working on nuclear power plants. You don't want to be making mistakes all the time in nuclear power plants. It's a bad thing. Why not write games? Much simpler, much easier, much less risk. So what about this? There are obviously a couple of clues here. If anybody can be more specific. No, all right, it's the Uniscope 300, obviously, made by Univac. This is from 1964. And also look at the aspect ratio. That's a 16:9 screen. 1964. And also particularly notice the presence of text. The screen was in fact a matrix of alphanumeric characters. Those weren't bit-mapped graphics. The device actually had a buffer which said, all right, on this bit we draw this letter, on this bit we draw this letter, on this bit we draw a space. So they weren't bitmap graphics. The machine itself knew how to print a limited character set in a particular way on the screen in cells. On this screen, in fact, you can see Mr. Benson and his account. You can see where it's all been credited and debited, and you can see where he was stung for $18,000 in tax, which probably hurt a little back in 1964. It was known as the glass teletype. And it's here that we start to enter familiar territory. We've got text on a screen. It's simply line-by-line character output. Did anybody ever use a teletype terminal? I'm guessing not. Okay. There was a guy in Poland. He'd used everything. Right, 1972, Pong. Anyone played Pong when it first arrived? Anyone old enough? Yes, at last. Hello. Nice to see you. So it hit the US territories in 1972. It brought games to coin-operated arcades. There were arcades long before there were coin-operated machines. I actually worked for a company called Sega, and they started off making Service Games of America. They started making electromechanical arcade games. But it wasn't until the 70s that we got video games. So that's an off-the-shelf cathode ray tube displaying simple vector graphics. That's not drawing text. It's drawing a line for a 1 and a line for the net in the middle, and drawing 5 lines for the digit 5. It's just line drawing and spot drawing. I was about 6 when I first saw a Pong machine. I distinctly remember it. It was in the hotel foyer of the Solston Hotel in Ottery St Mary. It made quite the impression on me. I was a big sci-fi fan. I was watching Doctor Who. And this was the very thing. This was the future incarnate. This was so exciting. I still write games. 1974 now. We're getting pixel maps. We had the release of the Evans and Sutherland frame buffer, which was 640 by 480 pixels. And so now we have, color pixel maps. That thing cost $15,000 for a 640 by 480 screen. Right, any guesses? I'm sure one of you will get this. Yeah? Yes! Fantastic. This one was actually rescued from a skip. The owner died, and his wife threw everything out, including that. And the people who went to the skip and did all the recycling, they found it, and they said, oh, hello, what's this? And they realized it was an Apple I. Auctioned it for $200,000. And they gave her half. So that was nice. They gave her half of that. But the innovation here was creating a composite video output that you could plug into a domestic display. That TV screen at the back, that was straight from Walmart, probably. The display was always an expensive part of the system. As I said, frame buffers at $15,000 is not trivial. But obviously, frame buffers got cheaper and cheaper as the hardware got cheaper. And home computers started to become a thing, really, about 40 years ago. This is the Atari 400. The clue is up there. It was known as Candy. Sadly, it was named after a pretty secretary at Atari. They were different times. The Atari 800 was known as Colleen for the same reason. But this was truly a consumer computer for the general public. It still made use of the domestic television, just straight into the front room. I'll just take a little diversion here. I want to talk about graphics cards and about early graphics cards. So this is 1981. Oh, did somebody say CGA? Yeah, that's it. This is CGA. This is fantastic. 16 kilobytes of video memory, 640 by 200 pixel resolution in 1-bit color. So I think 1-bit color is on-off, actually. But you could get 320 by 200 in 2-bit color. That gives you 4 colors. That's what we have there. You could get 160 by 100 with 4-bit color. And you could get a 4-bit color text mode as well. But in 1984, we had EGA, the Extended Graphics Array. This came with 64K of RAM, and you could add another 64K for better color resolution at higher resolutions. And you could even add another 128K, and that would give you multiple pages of graphics. So suddenly, double buffering has become a thing. 1987, yes, VGA. 256K of video RAM is standard, 640 by 480 by 16 colors, or 320 by 240 by 256 colors. Things really started to become photorealistic, apparently. Little did they know. VGA wasn't the end of it. We then had XGA, WXGA, FWXGA, XGA plus, WXGA plus, WSXGA, SXGA, SXGA plus, WSXGA plus, UXGA, WUXGA, which ran at 1920 by 1200, but none of them supported 1920 by 1080, which is the usual HD resolution. But you get the idea. More memory, more pixels, more color. I've missed plenty of cards out from the 1980s. I appreciate there were plenty more, but you get the idea. Just more. This is the first LCD display, 1987, the ViewSonic VP140. It was a lovely bit of kit. It was quite crisp. Sadly, that picture looks disgusting at this resolution. But I'm doing it no justice at all. But it really was quite a lovely bit of kit. But the LCD displays were obviously a leap forward from the cathode ray tube displays. They were digital, thin, crisp. You knew what you were getting. And so we are, well into the digital age. We've got DVI, HDMI, DisplayPort. They're all transmitting pixel information at a terrific rate across, fat cables. Before I tell you about the API, I should answer some common objections. No one will use it. Already, I've had considerable encouragement from educational institutions, from universities around the world, as well as schools in my area, believe it or not. As I said, the history of teaching programming involves writing simple games. With stdout, not so much, but with graphic output, there is a greater incentive to grab young people, get them drawing things, get them making games. There are plenty of libraries already. Yeah, loads. Lots and lots and lots and lots and lots and lots of libraries. I know quite a lot of them. But these libraries often come with licensing restrictions or platform restrictions. They'll only work on some platforms, or there'll be complexity restrictions. Who here knows OpenGL? Yeah. How long did it take you to learn? Less than a week? Less than a month? Less than 3 months? No. Okay. Still learning. So am I. 25 years on, I'm still learning OpenGL. And having a complex API affects your decision time. If you've got a problem to solve and you've only got a limited amount of time to solve it, you don't want to be deciding, do I have to learn OpenGL for this? Oh dear, that's not a thing you want to be thinking about. It will never be sufficiently performant. Well, depends what you mean by sufficiently, really. You should focus your optimization efforts appropriately. If you need maximum platform-specific horsepower, then no, this may not be the library for you. But only if you need maximum platform-specific horsepower. It'll run as fast as you need it to. Sorry, it'll run as fast as it runs. If you need something to run faster, then yes, you would need to go to another library. But we've got hardware running at incredible speeds right now. It's just a toy. No, it's not. It's not. This is really a variation of the first and third point. The thing is, this is entirely functional. It's suitable for a broad variety of applications. So be advised, as I said, the proposal document is nearly 150 pages long, and we're still making design decisions. In fact, 10 days ago, we checked in a whole new pile of stuff, which messed up this presentation magnificently. So, so you'll have to excuse me. But this really is, it's a bird's eye view of what's happening, okay? Now, I'm an English mathematician. Can you tell? That's how I spell colour. You know what's going, don't you? Yes, that's not how the ISO C++ standard spells colour. I was quite grumpy about this. I'm a bit of a stickler for spelling. But our first class is RGBA_color. And now this consists of 4 pieces of data. I expect you can guess what those 4 pieces of data are. The red channel, the green channel, the blue channel, and the alpha channel. Alpha is the amount of transparency. Is there anybody here who's not really done much graphics who thinks, alpha? What's alpha? Oh, okay. That's fine. Good. I will adjust accordingly. Graphics, it really is a huge subject. There's a broad variety of levels of expertise, and when doing a graphics talk, it's very tricky to know where to pitch. You know, am I talking about people writing, you know, shaders to do peculiar things or not? Now, the values of those RGB, they're floating points, but they can be set in red with integral values as well. And there's also a set of standard colors, which conforms to the CSS colors. Okay? Color. Simple enough. Naturally, we need some linear algebra support. So we have a point, we have a matrix, and we have a display point. So the point is the model. The display point is where it goes on the, you know, where it fits on the screen. All of these are templated over a maths trait type. This was the new feature that went in 10 days ago. We'll come on to that in a moment. We have a little bit of geometry. We've got a bounding box, and we have circles. Now, these types are used elsewhere in the library. We don't intend to specify a full geometry library. That would be a bit foolish. We've just specified what we need to do the things. It would be nice to specify. It would be nice to see a full linear algebra library in the standard, to be honest, because lots of people get that wrong a lot of the time, which I think is a good reason to put something in the library, because everybody else gets it wrong. So I look forward to that appearing in due course. Now, when I joined the project, everything was done with double precision. This isn't very graphics card friendly, so we migrated to float. But then it became clear we could go even further, and we could create a customization point for all the maths. So we have this things like DirectX Math. It has its own hardware-backed way of doing the mathematics. So the vendor will obviously have to supply a default implementation for the platform. So on Windows, I imagine it would be DirectX Math based, or they might also supply a software version. It'll be up to the vendor. And of course, we have text. Text is hard. We don't actually have text. More on this later. Now, the first thing we need to be able to do is to draw lines and curves. That's it, 2D, lines and curves. So we have a class called Path Builder, which acts as an instruction buffer. Okay. And we add what we call figure items to a path builder to draw things. So these figures are a combination of administrative types like new figure, closed figure, as well as instructions such as line, arc, quadratic curve, cubic curve, the Bezier curves with control points. And the interpreted path, that class contains the data that results from interpreting a sequence of figure item objects, of executing the commands. Again, this is templated, but over a different type, graphic surfaces. This is another part of the change that went in 10 days ago. Now, this proposal started life as a Cairo wrapper, so, several years ago. But during the past summer, we made the renderer a customization point. So you can put anything in. You can create a graphic surface object for DirectX, for Vulkan, for OpenGL. Well, I say you can. You can implement one if you like. Hopefully, your vendors will do that for you. Hopefully, OpenGL will do that for you, or will hire someone to do it for them. Now, a typical use case for a 2D API might be rendering a PDF document. It's a good stretch for a 2D library. PDF is a standard. It's an ISO standard. It has been since July 2008. And it's a well-defined target. So we think we can do that with all of this. Of course, we've got brushes for filling chunks of the screen. We have wrap modes, which dictate what happened when you sample outside of the brush. We've got filters, which tell you how to deal with sampling from a pixel map. So do you use the nearest color or bilinear filtering, or that sort of thing. So there are 4 brush types. There's a solid color, kind of a linear gradient. It goes from one color and smoothly transforms to another. We've got a radial gradient. That's what the circle is for. We have a color at the middle, which changes into another color at the edges. And a pixel map surface for bumping bitmaps onto the screen. More from brushes. We have a gradient stop, and that's the point at which a color gradient changes from one color to the next. And gradients are actually formed from a collection of gradient stop objects. The brush class, it's an opaque wrapper for graphics data. That's the best way to think of it. The data is immutable. But it's usable with any surface or surface-derived object. Surface, as you see, that's the thing that this is the monster. So first of all, we've got a series of enum classes that describe options for properties of the surface. So we have anti-aliasing, none, fast, good, best. We've got a fill rule for. I'm running short on time. I'm going to zip through this. We've got line caps and line joins. So line caps are what's at the end. Line joins is how lines will join. What will happen when lines join together. And we have a compositing operation. There are 29 compositing operations that we require. And they're mathematical formula for what happens when things overlap. Moving on, we've got some more. We've got the pixel format. So the pixel formats we support are ARGB32, so that's alpha, red, green, blue on 32 bits. We've got RGB24, 24-bit representation, RGB16 as 565, and RGB30. We have scaling. What happens when the size of the back buffer is different from the size of the display buffer? Do you stretch it? Is it in a letterbox? Do you do nothing at all? We have a refresh rate, which is either refresh as needed, refresh as fast as possible, or refresh at a fixed rate. And we have the image file format. Again, these are standard file formats. So we have PNG, JPEG, and TIFF, and an unknown file format for all the others. So now we have some property classes that collect all these together. We've got render properties for anti-aliasing and compositing. We've got brush properties for the filter mode and the filter and the wrap mode and the fill rule. And we've got clip properties which describe the area to be rendered and which offers a fill rule. The stroke properties, as I said, big paper. They cover the line styles, such as the width and the cap and the join. We've got the mask properties, which describes the area which is not to be rendered. If you want to mask something off, there'll be mask properties. And finally, we've got a utility class for drawing dashes, which comes in surprisingly handy. And finally, we've actually got the surfaces themselves. We've got the basic image surface. Now, this provides an interface to a pixel map. Okay, so there's your that's your picture, that's your GIF, your animated everything. That's your collection of pixels. You've got your basic output surface. Now, this provides a surface you can draw to. There's a message queue. There's everything you need to be up and running. This is the equivalent of the standard output, but in 2D. Okay? But also, we have an unmanaged version, which allows you to create your own window class and do all the, to specialize further. Finally, input. Coming soon, like text, this is actually quite hard, although a little easier than text. So as with basic strings, some defaults are defined. So in the reference implementation, we actually have a class called graphics math float impl. Okay. We've got a class called chirographic surfaces, which is templated over our default graphics math. Math, not maths, because it's American. So this gives us typical names like point 2D and brush. So point 2D is a basic point 2D using the default graphics math. Brush is a basic brush using the default graphics surfaces. So like basic string and string, we have basic brush and brush. And also we get our output surface. So that would be the concrete type of the default standard 2D output. We're still looking for a name. Cout, cout, that's quite clear, character out. But the trouble is, we've either got gout or grout. They don't really fly. Neither of those went down well. So if anybody thinks of a better name, we really are all ears. We've spent an absurd amount of time trying to come up with a name for the standard graphics output. But the fact is, with its default graphics surfaces, vendors will need to supply a graphics library. Okay, I imagine Microsoft, as I said, will take the DirectX route. Others can, supply their own. You can override them. Customization points, that's where it's at. So let's look for a few examples. 4 are quite simple, and the last a little more complicated. But the first 4 all start with this block of code. Okay, so we make an image surface, and a back brush, and a foreground brush. We turn off anti-aliasing. Do tell me if I'm going too fast. I'm hoping this is quite clear. We make a path builder. We paint the surface with the background brush. Sample code goes here. And then we save the sample using the image file format PNG. So there we've got a demonstration of quite a lot of the housekeeping that would just get something up and running. Okay? 8 lines of code is nice. I don't know if anyone's done any DirectX programming, but actually the amount of code from, yeah, you have, haven't you? Yeah, the amount of code from when you hit main to when you put something on the screen, it can be pages and pages of the stuff. Right, so the first 5 instructions on this one work on the path builder object. So we create a new figure at 8020. We draw a line. Then we draw a line relative to that. Do that again. And close the figure, and then we stroke that path onto the image surface. Okay, 6 parameters there. I won't go into them. So let's just look at this again. New figure at 8020. Then we draw a line, 220x, 20y. And then we draw a relative line, 60x, 160y. Then another relative line, minus 260, 0. And then we close the figure. Any guesses what that might draw? Somebody said triangle? No. Close will indeed draw a line back to the origin, but what will the whole shape be? Everyone's doing this. It's great fun. No one seems to be quite getting it. All right. This is a little unfair, to be honest, isn't it? That's what you'll see. Hello, trapezium. Okay, let's try something else. We're going to draw 2 things now. So here's the first. We draw a new figure. Relative line. Relative line. Relative line. Okay. 100 to the right. No change up or down. 160 down, 100 left, okay? And then back up. So here's the second. We draw a figure and some lines, close the figure and stroke it onto the surface. Right. Back to work, apparently. Our lunch hour finishes at 1:45. Should have turned that off. You wouldn't believe I've been giving presentations for... Anyway, hands up. Who's expecting 2 identical rectangles? Oh, look at you. Oh, okay, who is not expecting 2 identical rectangles? Logical exclusion. Who is scared and wants to go back to the teletype? Yeah, yes. I'm old. I don't like change. I want to... All right. That's what you get. Not quite identical. What happened there, then? Well, the first is an open figure. Do you remember we didn't get a closed figure? whereas the second is a closed figure. So the first figure's ends are closed by the line cap property. Okay? There's caps on the ends of the line. We're actually drawing a line with two ends. Whereas the second one, because it's closed, then the ends of the figure are controlled by the line join property. Okay? By default, this is mitre. Let's try some curves. First, a quadratic curve. Okay, so this Bezier curves. Okay, Bezier curves have a control point. Let's just leave it at that. Okay, so I'm not going to do geometry here. So we have a quadratic curve with a Bezier with a control point. Move to another position. Draw another one. Notice how it's exactly the same. Rel quadratic curve, but starting in a new position. This time we close it. Okay. Now we move on to another figure, a cubic curve, two control points for a cubic curve, and another figure, cubic curve, close that one. Draw it. That's what we get. So that's a quadratic curve, and then a closed quadratic curve, then a cubic curve, and a closed cubic curve. Okay? These are Bezier curves. They have a well-defined parametric representation. You'll make a lot of use of them. Let's try something a little more exotic. Right. First, we create a scaling matrix. Now, this shrinks in the x-axis and stretches in the y-axis. So we create a starting point for our shape. Oh, look at that. We're taking into account the scaling factor here. And then we apply the matrix to the path builder and start a new figure. So we draw an arc of 3 pi over 2, starting at a quarter pi, half pi over 2, and then we stroke it. Now we clear the path buffer, start again with a new figure. Draw some lines, quite a lot of lines, and some more lines. Close the figure. Now we do a fill. Okay? Now, for the cunning part, we put a translation at the front of the path buffer, and then we fill the region again. Hello, C++. See, we actually do have text. Actually, you may laugh. The way that text is done is simply by drawing lines and curves. That's all it is. So we are ready to go with text. What we really need in the repository, and I will award points for the first person to do this, is somebody who can submit a Hello World pixel map image to the repository. That would be very welcome. So our final example is, it's more exotic. It's a computer game. It's a version of the Asteroids game released by Atari in 1980. It's the fizz-buzz, really, of computer games. It's a very simple game, but it does quite a lot of things. It's a lot of fun. People recognize it straight away. It's why I've done it. So let's start with the maths. So we have a standard to represent Cartesian coordinates. But the nature of the game requires polar coordinates. By the way, does everybody know what the Asteroids game looks like? I've just realized I'm assuming you've all played it or you're all familiar with it. Right. I know, hang on. I'm about to break the fourth wall. Here's some code. Yes, I'd like to build it. Oh, no! Wow, that's amazing. That worked this morning. No, it did. It really did.
It's not already running, is it, perhaps?
It's not already running. A task was cancelled. Hang on a minute.
You can see it in the Berlin Computer Games Museum.
Yeah, I'm sure you can. Or, this is bad news. Okay, what I'm getting here is a task was cancelled. Anyone know what that means?
time settings can change from UK to German.
And that can cancel a task in Visual Studio.
Yeah, I had the issue on my computer at work.
So, right, okay, do you know what I'm going to do?
Then Visual Studio doesn't like it, and that's exactly the message I get.
Do I need to restart Visual Studio?
Visual Studio is the only solution I've found so far.
Okay. I'm absolutely delighted you're in this room. Thank you very much. So is that Microsoft's fault then? Or is it Visual Studio's fault? Actually, Visual Studio is also Microsoft, isn't it? So sorry about this. Doo-doo-doo. Oh, the slowest 5 seconds of my life. Right, let's try. Oh! Yes, this is working, sorry. For some reason... There we are, Asteroids. So that's Asteroids. Let's actually play a little bit of Asteroids, shall we? So you can see what the idea is. So there's that guy in the middle, running around. Ooh, look at that. Hey. Oh, nope, right. Can shoot at things. Oh, collision detection. Oh wow. But you get the idea. I've got collision detection working. If I can just hit something. Oh. There we are. That's Asteroids. So I hope that gives us a little bit of context for the rest of this talk. Now, moving on. So as you can see by all that rotation, the nature of the game requires polar coordinates. So we've got a polar class. And we'll also require conversion between the two, between Cartesian and polar coordinates. Awkwardly, they're both pairs of floats. Polar coordinates and Cartesian coordinates are both pairs of floats. So that could be confusing. Perhaps we need an angle type. Who's heard of tau? Fewer people than I expected. OK, tau is 2 pi. Okay? I think pi is silly. And actually, we should... No, I do. I think pi is silly. We should use tau. Tau is 1 turn. There we are. Why have we got a half turn? Why? What's so special about a half turn? Anyway. Tau is 2 pi. We define tau, okay, because we can, because it's our paper. And it means 1 turn. We've got to manage collision detection, obviously, so we do this with a function called intersects and contains. All right. In addition, we need to worry about things like the radius of objects, and we want to rotate them. We need to rotate the spinny man in the middle. And obviously, we want to move them about, otherwise it would be a very dull game indeed. Next, we have to consider the physics. What we're doing is building a model of the universe. It's a very, very simple model, but nonetheless, it's a model of a subset of the universe. And then we're drawing it every so often. So how do we model the asteroids in the ship? With a path buffer. Okay? It's easy to turn a path buffer into a set of draw instructions, obviously, because you're saying, oh, here, 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 close. And we also define a collision structure, which tells us everything that we need to know about an object to worry about collision, which needs to be a little different for rotating objects. Our regular objects that we're modeling have an update function, which updates their position according to their velocity. Some objects need to deal with being divided. Well, the asteroids, actually, need to deal with being divided. And then to draw the things, we need to know their position. And we also expose the velocity. Objects that can be controlled respond to thrust. This changes their acceleration. And they can be spun, and that changes their orientation. So, looking at the asteroid, we want to update this. We want to update its physics, its position on the screen. We want to draw it, and we want to expose its collision data. The ship is similar. Update, destroy, and draw. We've got missiles. Update, destroy, and draw. Can you see a pattern emerging here? And we also want that collision data as well. We don't need the ship collision data because that's what we're saying. What are you colliding with? So we've got asteroids, ships, missiles, and the physics to model them so we can make the game. Oh, look, an update function and a draw function and a generate level function. Because we need to actually start a game, and when we finish destroying all the asteroids, we need to give them some more asteroids, only more asteroids. We start off with 4 on the first level, and then 6, and then 8, and then 10, and it never stops until you are eliminated. Right, let's consider input. We need to get the key states. We need to get the individual instructions, fire, thrust, spin clockwise, spin anti-clockwise. Oh, hyperspace would be handy as well. Must remember that. Finally, we need to worry about our host operating system. In this case, it's Windows. So we just need our key definitions, which key does what. Something to get the key states, an entry point. So let's look at some source. There we are. So this is our maths header. We've got polar coordinates. Nothing controversial there. R and theta, private data. We have a class called stadium. Who's heard of a stadium before? This is an object in geometry. And if you've ever seen the film Ben-Hur, which features horses rushing around a stadium, around the Circus Maximus, it's like a rectangle with rounded ends. It's called a stadium. It's officially called a stadium. That is an ISO name, stadium, I believe. I thought it was called lozenge for a long time, but you know, stadium. Right, we define an eighth of tau. Because we define tau in the paper, but I'm defining eighth of tau here. We've got some useful geometry algorithms, minimum distance from line segment, whether 2 lines intersect, defined by their endpoints, or whether 2 bounding boxes intersect, or whether a bounding box contains a point. We've got converters between polar and Cartesian, and we've got a radius function, and we can rotate and translate things. We also have some inline implementations, but they're all quite trivial, as you can see. They're just accessors, but I don't like defining code inside open namespace declarations, and I think nobody should do that, because there's no way you can tell in there that you're actually in a particular namespace. So all my definitions are out here, and they're all tiny. You know, the conversions are it's single line stuff and constructing the stadium. So I hope you agree that's reasonably simple. We can look at the implementation. So the Intersex function for a stadium is quite simple. You've got a line segment in the middle, so you want the minimum distance from that line segment. If it's less than the radius of the stadium, you're good to go. And then but this is all really just maths. This is straight off the web. There was no hard work required here other than just copying code off from somebody else, which is often the easiest way of doing things. It's just all easy stuff. All of this stuff is in the repository. I'll give you a link to the repository at the end. Let's move on to the physics header. So we have position, velocity, and acceleration. These are vectors, but they're 0.2D. Now, our path buffer. Now, all of our objects have 14 points or fewer. Thank you. All our objects have 14 points or fewer. So it just makes sense to have an array of 14 points and say, right, that's our path buffer. And something to describe, to say how many points are actually meaningful in the path buffer. It's just faster. It's probably not memory optimal, but frankly, the amount of memory I'm using up is pathetically small. Then we have our collision detection, our collision structure. So we need to see what the bounding circle is for that collision object, where it is, you know, where it sits, and what its path is. And here we have physics. Update. We'll take a time parameter. If we're updating something that can be accelerated, that will take an acceleration parameter. There's our divide function. Lots of random numbers there. because what we're doing is dividing the asteroids, and we don't want it to be predicted. We don't want it to be predictable about where they're going to go. So we have a position and velocity, and controllable physics that has a physics member, but also allows you to apply thrust and spin. So besides exposing position and velocity, we're also exposing acceleration and orientation. And some useful functions again. Sorry. It's getting a bit full over here. Just for a moment. So these constraint functions, they put a cap on the position because we want them to, once something goes off the screen, we want it to come back again. So we actually constrain its position in the universe as well. And the same with the velocity. We're accelerating this ship as it moves around. You don't want it to just go endlessly fast. We want it to have a top speed. And also we constrain the orientation between naught and tau. It's just easier like that. We have a function called screen space. The difference between engineers and mathematicians is right-handed and left-handed coordinate systems. So for me, if I draw a graph, then and I increase the angles, it goes around like that, like a protractor. If I'm an engineer, it starts at the top and goes around like a clock. It's very annoying, but that's just the way it is. Do you know what? If clocks had been invented in the southern hemisphere rather than the northern hemisphere, clockwise and anti-clockwise would be the other way around. Because the only reason clocks go around that way is because that's the way that sundials went round in the northern hemisphere. Anyway, little things that bother me, sorry. And finally, we've got some collision testing functions and some, again, some trivial inline implementation. Just all returning stuff, all simple accessor functions. And then we can look at the implementation here. Quite easy. So updating the physics, position plus velocity times time. Is that rocket science? It's not. It's Newtonian physics. Rocket science generally deals with mass changing over time, because as fuel is expended, then an object becomes lighter, which affects the trajectory. Anyway, I suppose it is rocket science in a way. It's rocket science today, isn't it? Yes. Yes, it is. And so if you want to update something with acceleration, then velocity is acceleration times time. Again, Newtonian physics. It's all quite simple. The reason why I keep saying it's all quite simple is because you can teach this stuff to a 14-year-old. And that's kind of the significant point I want to be making here. Teaching C++ to kids is non-trivial. I have 3 children. None of them have learnt C++. They're going to watch this video and they're going to cringe with embarrassment because they know that they have not learnt C++. And I am disappointed. Anyway, here's our divide. What we're doing is we're getting the velocity of the thing that's coming in, r. So we're getting the polar representation of velocity. So r gives us our speed rather than our velocity. And then we can calculate some angles that are different from that, shoot them out. It's marvelous. Updating our controllable physics over time. Yeah, we reset the acceleration. This is because when you thrust, when you're playing the game and you press a button, you want it to keep accelerating, but you want to reset so that if you take your finger off, then there's no additional thrust being added. That wasn't even remotely clear, was it? I'll move on, hang on. Time is short. Path from prototype, we want to make, we've got shapes that we're effectively reusing time and again. So we start with the prototype and say, well, I want to make an asteroid from this path. And then constraining the precision, we're looking at whether or not something is outside of the playing field. If it is, then we bring it back into the playing field. Constraining the velocity, make sure that things are traveling at an appropriate speed. And then collides, this is a simple function. Again, what we're really doing, without using a for loop, is iterating through all the parts of the path and seeing if it's colliding with all the parts of another all the paths of another item. The next thing to look at is probably the asteroid class, because we're running short on time. The reason why the asteroid class is significant is because we're going to start drawing things with this class. So we have our asteroid destruction and our asteroid class, update and destroy. We get our collision data. And here's where we use the stadium to get the sweep of the asteroid. Over time, the asteroid will draw, the boundary of the asteroid will draw a stadium, circle at one end, swept in a straight line, which means that when the ship is destroyed, we can see if we're going to put it back into the path of an asteroid. Because you don't want to do that, because then it would get destroyed again. More trivial stuff, but here is our draw function for the asteroid. So it's our path builder. We clear our path. We get our position, add the first vertex to it, flip it through screen space, and then for each of these, we draw a line to the next vertex. We close the figure, and then we stroke it. That's it. But I'm going to move on. I've taken a little longer than I was planning. As I say, all this source is on the repository. I've taken it straight from the repository. It's not there. Take a look yourself. I'm open to pull requests. I'm open to criticisms about the quality of my C++ programming. You know, we're all here to learn. I've only been at it for 30 years. Right. Things that we have to do. We have to add text and input. And we should write more renderers for OSs to prove that the display surface and the handler classes, to prove it all actually works. We need lots of sample programs as well as the renderers. The best way to show this all working is to actually write some games, write some simple stuff. And the mission of exposing C++ to kids and getting kids learning this thing is best served by giving them lots of things to start with. So welcome to more sample. Welcome to receive more sample programs. Sound? It's not part of the paper, but it's part of the human-machine interface sort of issue. I'm a bit busy, but I have actually started conversations with Guy Somberg, who wrote Game Audio Programmer. And he gave a talk at CPPCon. We started a conversation. We think we might, it's a multi-year project. All of these big proposals are multi-year projects. But it would be nice to move on to sound next. Because that's obviously the one thing that's missing there. I know that in space no one can hear you scream. But, we're on Earth, really, aren't we? You want the pew, pew sounds. Open to questions. Thank you. Right, there is a microphone lurking around. Ah, there we are. Thank you very much. Does anybody have any questions? At the back first.
Thank you. So I was wondering whether you considered using something like RAII instead of closing a path explicitly, because it sounds something like error-prone. And also was wondering why do you, so I do understand that you do not want to have a full-fledged linear algebra library instead of this proposal, but I was wondering why do you constrain the existing types and algorithms to 2D matrices and points, because this way once we, for example, look into 3D, we need to have new type names for the 3D variants.
Okay, this is a starting point. I understand your question. Yeah, path builder close. We probably could write a wrapper class for it. That may indeed be a hangover from the way that Cairo did things. The design is still in action. That is a really good point, actually. Anything that requires a close is crying out for RAII. So I'll consider that. As for restrictions, we've got to stop somewhere. We've got to provide some boundaries. Shipping is a feature. These things can be changed. It's harder to change something once it's in the standard than it is before. But we have to balance. As I say, this thing's been running for, I think, Mike McLaughlin was he started this. I'm just co-authoring on this with him. He started this 4 years ago. It really is about time that we just ship something, because as I said, we haven't even done text or input, and that's something that people seem to want as part of HMI. Do raise issues on the GitHub. I really do mean that. I'll just put that back up again. That's the GitHub. Do raise issues on there. We are dying to hear from people, because if you've got issues and you decide not to raise them until it's into the standard, you've made life so much harder for everybody straight away. We want to hear them first, as soon as possible. And I'd like to hear your issues and your reasoning and write it down, because then we can refer to it. Have I made it clear? Please give us issues. Thank you. More questions? Yes.
Yes, my question is regarding standardization. As I understood it, your main point was that having a 2D library in the standard is great if you're teaching C++, because games are a great way to teach coding, which I totally agree with. But if you're in an environment where you're teaching, don't you already have like a way to set up the development environment anyway, where using an external library isn't that big of an issue?
Using an external library isn't that big of an issue. You see, that's the key point. I know what you're saying. Using an external library, it isn't that big of an issue, but it is an issue. You're relying on tuition texts that are based on that library. If everybody knows, right, I'm teaching C++, right, here's everything you need to know to teach C++, which includes everything to teach, the standard library, everything to teach the graphics library, then you have standard tutoring texts. It will be quicker for best of breed teaching texts to emerge if there is a standard against which there is an expectation. But if you've already got your own set of teaching texts and you've got your standard library, and you've already got your library that you teach against, great, do that. I'm not suggesting that you don't. And also, as I said, it's not just teaching. This does work. There's things like audio spectrum analyzers. I'm trying to work on an audio spectrum analyzer that works in real time. That's a thing that can be done. You can draw UI. There's plenty of reasons. No, that's fine. That answers your question, doesn't it? Next. Got 3 minutes.
So I was just wondering what platforms the reference implementation supports.
Windows, Mac, and Ubuntu, and Linux.
And Windows.
Sorry?
You showed it already on Windows, so
yes.
I expect. Okay.
Yes. I'm sorry, I haven't been keeping track of order.
Hi. So it seems like what you've got in the to-do list, text, input, sound, is kind of the building blocks of a game engine, basically, a 2D game engine. All the, unless you have a reference implementation of the main loop and stuff.
It could be construed that way, yes.
Yep. So I'm just wondering, is the intent with the standard to just do 2D rendering and stop there? Or is it to build on that and have more of the building blocks for what could be considered a...
I'm not going to suggest what the intention of the standard is. Okay. A graphics library for 2D was requested. We're delivering that. I think if they ask for a 3D library, I might become a lumberjack or go back to... I was on theatre before I was in programming, so I might go back to the stage. I wouldn't like to run a 3D standard through. It might be done. There might be greater... Well, I know there are greater minds than mine that might be able to do that. But I don't think the standard is going to look any further ahead than... than this TS. You could build I would hope there would be enough to build games out of. That there would be, once you've got input and sound and things like that, then yes, you can build games and you can build all sorts of things. If somebody wants to propose a 3D standard, it's a lot of work. I mean, this was a lot of work, but 3D, that's a lot of work. It's a big lot of work. So.
I was just more interested in what the kind of limitations of the standard were. Whether it was just 2D rendering or whether it included like a game loop and sound and stuff like that.
The standard's not going to put a game loop in. I mean, you're not going to get a game engine in the standard. Oh, session's over. Right, sorry. Okay, you're not going to get a game loop in the standard. But make a proposal and see what people think. The committee is only made up of people who turn up. Okay. Thank you everyone for coming.